Hey everybody, and welcome to this video on section 5.4, the first day of it. We are doing class this way because I have to go to a teaching presentation for a job candidate. So recall that we already covered this first page on Monday, so I'm not going to go over it again, but just to reset where we are, we stated the central limit theorem and did this example to illustrate what it's saying. So just as a summary, if you have a bunch of random variables with the same average and standard deviation, if you add them up, you get something normal, even if these variables are not normal themselves, and you can say what the expected value and standard deviation are. And similarly, if you take these variables and average them, you get, again, a normal distribution, even if these variables were not normal to begin with, and you can say what the average is, and you can say what the standard deviation is. That's what we covered on Monday. Let's look at a couple of applications of that. On some level, the entire rest of this chapter is applications of that theorem. It truly is the fundamental theorem of statistics. So these are just kind of warm-up applications. It's also worth pointing out that some of the applications we will do, we could also have done in previous chapters. But we're going to use the central limit theorem and the continuous framework to answer the questions now. So somebody claims to have flipped a fair coin 10,000 times and got 5227 heads. Is this claim believable? First of all, note this is kind of a toy example. Most likely nobody is flipping a coin 10,000 times. But this is a warm-up example for the next example, which is real, not a toy example, the next example. Also, I just want to start with something friendly, like flipping a coin. Also, we are now evaluating a truth claim. That's what statistics is all about. Somebody has claimed that they did a thing or saw a thing, and you're going to try to statistically evaluate that. That's what this example does. So to test a truth claim like that, we're going to ask this question. This is the kind of question that classical statistics asks in order to evaluate a claim, like fair coin. Let's assume the coin is fair. Assuming the coin were fair, what is the probability we would see this kind of thing? 5227 heads out of 10,000 heads. So somebody has made a claim. They're essentially claiming that the coin is fair, and then they got some data. So you're analyzing an underlying claim that the coin is fair. So you're not directly investigating that claim per se. So you're not asking what's the probability the coin is fair. You're asking, okay, assuming your claim is true, like assuming I'm going to go with you for a minute, right? I'm going to enter your world and assume your claim is true. What's the probability I would see data like what I'm seeing? That's the kind of question you will ask to evaluate these claims in Chapter 5. In the terminology of statistics, this claim, the coin is fair, is called the null hypothesis. So every sort of hypothesis testing question in this chapter has this form. Assuming the null hypothesis is true, what's the probability of seeing data like what is being claimed? So let's analyze that. So we need to think about, assuming the coin is fair, what's the probability I would see that? And we're going to use the central limit theorem now. So to use the central limit theorem, notice I'm flipping a coin 10,000 times and summing the number of heads I get. So there's some kind of summation there I can keep track of, and that's what I'm going to do. So x will represent the result of a single coin flip. I'm going to let x equal 1 represent the outcome of heads, and 0 represent the outcome of tails. So notice the expected value of x is a half. Why is that? Because we're averaging 1 and 0, and they are equally likely. So the average flip would be a half, like halfway between a tails and a heads. And the standard deviation of x is given by this formula here. Outcome minus average squared times probability plus outcome minus average squared times probability. The average and the probability happen to be the same, but it's just a fluke. And then you take the square root of that, and it turns out that the spread of x, sigma of x, is also 0.5. So don't be thrown by all that. Like it's not as if every average and every standard deviation are equal and they both equal 0.5. It's just a feature of this example with coin flipping. So now let me define the variable of interest. So X is a single coin flip. So you can get one heads off of X, or no heads, but you could get one heads. So now consider this variable here. Let's add X to itself 10,000 times. What are the possible values of X? The possible values of X is any number between 0 and 10,000 corresponding to the number of heads you flipped. Because each new head you get, you're adding 1 to a running total. So this Y is the variable we care about, and we're asking ourselves, assuming the coin is fair, what's the probability you would observe at least 5227 heads? That's what that's saying. So we need to calculate that probability, assuming a fair coin. And notice we're picking off a tail of data. We're not doing P Y equals 5227, because Y equals a particular value, that's going to have negligible probability, be tiny, no matter what this value is. So we're thinking about what's the probability of seeing a spike like that. Like we expected 5,000, we got 5227. What's the probability of seeing a spike like that? Similar to Poisson questions we did in chapter 4. So where does the central limit theorem come in? So Y is the sum of variables X. So whenever you're summing variables, if these individual variables have the same expected value and same standard deviation, and each copy of X does, because they're literally the same variable every time, if you do that enough times, you will get a normal distribution. So the central limit theorem says 3 things here. It always says 3 things. It says this summation variable, first of all, is a bell curve. Also, you know what the expected value is. And here, notice, we're not averaging. We're just keeping a running total. So if I come back up here, central limit theorem part 1, there was no average here. I'm just adding a bunch of stuff up and not dividing by n. Then we know we get something normal. Excuse me. We know what the average is. We just take the sample size times the original average. And then we know what the spread is. The original spread times the square root of the sample size. So we get 3 things. Bell curve, we know the expected value, we know the standard deviation. I then list these 3 things. So sample size was 10,000. The original expected outcome was 0.5. So unsurprisingly, we would expect to see 5,000 heads in 10,000 flips on average. The standard deviation is the original standard deviation for X times root 10,000, which turns out to be 50. So this variable here, this Y, keeping track of the number of heads we get in 10,000 flips, that variable is a bell curve centered at 5,000. The standard deviation is 50. So I've set up the integral here, but notice we recall from class that anything more than 3 standard deviations away, the probability is vanishingly small of seeing that. Recall that from a previous class period. So by the time you reach 5150, you're pretty much out of data. So, the probability is very small of seeing 5227 or more flips given a fair coin. If you want to see this in the calculator, let me show you what it does. So the mean, 5,000. Standard deviation is 50. I want to do above 5227. Okay, so 5227 is like over here somewhere. The calculator here doesn't go beyond 4 decimal places. That's why it's saying 0. The integral will pick up, 10 to the minus 6. You don't have to do the integral if you don't want to. I'm including it for completeness. So a bell curve centered at 50, tapering off steps to size 50. By the time you reach 5,200, there's nothing left. Okay. So what does that mean? If the coin were fair, the probability of seeing the kind of data we saw is extremely small. So the smaller this number gets, the less we trust the original claim. So the idea that a fair coin could somehow get you 5227 heads out of 10,000, that's extremely unlikely. So you would doubt that that claim is true. Now notice this is a probability here. On your next exam, you will be asked to interpret this number. What does this number mean? That pops out at the end of this process. So here's some language for you. In this particular context, it's this. It's the probability of observing the kind of data we saw assuming a fair coin. So I put this in bold here, that 2.81 times 10 to the negative 6, that is not the probability that the coin is fair. It is the probability of observing 5227 out of 10,000 flips, heads, assuming the coin is fair, given a fair coin. So the number is kind of a backdoor way of trying to evaluate the truth claim. Like, I take your claim seriously, I enter your world, and then I ask you, inside this world, what's the probability I see information like this? And it's not likely. Anyway, that number is called a p-value, and we're trying to determine whether we should reject the claim or not. And so basically, the smaller the p-value gets, the less likely the claim is to be true, like the more we doubt the claim. And so you can ask yourself, like, how small does this number have to be before we call shenanigans on the claim? And in statistics, the classical thresholds are 5% or 1%, depending on who you ask. 5% is pretty standard. But regardless, something like this is much smaller than 1%. So the smaller the p-value, the more we doubt the claim. And eventually we have to decide if we're going to reject the claim or not. So we just need a threshold set. So here's an example of the central limit theorem, giving us a normal distribution, which allows us to use the normal distribution stuff, get a probability, and we can then reject or not reject the original claim. Let me show you one more example, which is definitely not a toy example. This is real. What I'm about to show you is basically how any vaccine or drug trial presents their data. It's not maybe so streamlined like this, but if you look at like documents that Pfizer published after their vaccine trials for COVID, you're just going to see this kind of thing, this kind of work. So this now is real right here. And this clinical trial here, this is real. These numbers are accurate to the trial. Okay, so in one of the clinical trials for the polio vaccine, they actually had 400,000 children in total in that trial. It's a lot of people. So 200,000 children given the vaccine, 200,000 in the control group. And here are the results. Of the 200,000 who got the vaccine, 57 eventually got polio, and that number was 142 for children who did not get the vaccine. So polio is just, despite maybe how large it looms in the public imagination when we think back to the 1950s, it just wasn't that contagious. So just really not that many people got it. It's just that of the people who did get it, they sometimes got put in an iron lung and could never walk again. And of course, FDR had polio, so it has a large presence in the like collective imagination, but it wasn't that contagious. So it's not like everybody was getting polio and then getting paralyzed or something. Anyway, given this information, do we have evidence that the vaccine is effective? If so, is that evidence good, or is it kind of weak? So let me walk through real quick 3 possible reactions to this trial data that I just presented. You could just say, look, we ran a trial with 400,000 people and only 199 got sick across the 2 groups. That's a tiny sample size. So like, we just don't have enough data. What we should do is run trials with millions of people. So these numbers of infected people can get higher. And then we'd have more data from sick people. So you could just say, look, like, I appreciate your 400,000 person trial, but we don't have enough data from people who got sick. That's one reaction you could have. Here's another reaction. Clearly, the vaccine was effective. Look, did you not see that 57 is smaller than 142? Did you not notice that? So obviously, the vaccine is effective. That's reaction 2. Reaction 3. Obviously, the vaccine was not effective because we gave the vaccine to some people and they still got sick. You know, there are many other possible reactions you could have. But the thing about statistics is it can cut through all this. Like, which of these reactions is correct? Any of them, none of them, whatever. Statistics will tell you how to react to information like this. First of all, before I do this real quick, let me just point out, reaction number one turns out to be false. It's a natural reaction, but this actually has plenty of data to make a conclusion, interestingly enough. Reaction two is a bad reaction because what if this 57 were like a 100 and that was like a 101? So even though 100 is less than 101, those are pretty close. That's not strong evidence of effectiveness. So you can't just literally be like, that's smaller than that, so I'm done. Reaction three is actually fairly common nowadays regarding COVID vaccines. Like, oh, I know people who got the vaccine but still got COVID, so the vaccine must not be effective. When people say whether a vaccine or a drug is effective, they're not saying it's foolproof in this context anyway. What people are saying is that it's better to get the vaccine than not. So the vaccine has some sort of protective power. So here it's just like a language error. Like in this context, when you say effective, you're not saying it prevents all infections. You're just saying it provides some protection. Okay. So anyway, so in a drug trial of any kind, vaccine or not, the null hypothesis is always this. The vaccine is not effective or the drug is not effective. Why would that be the null hypothesis? Because the null hypothesis is the default. So if you want to bring a new vaccine or drug to market, you have to prove that it's effective. So we default to it not being effective, and then you have to overcome that. So it would be bad if we did it the opposite way. If we assumed everything was effective and then we had to prove it wasn't effective, that's asking for trouble, you know. So we assume not effective and then we have to prove otherwise. So the drug trial then needs to provide evidence that this is false. It's not effective. So you have to pay a price in double negatives there, but that's what you're doing. So let's let X represent the result of a single person who got sick. We only care about people who got sick. And so we'll let X equals 1 if the person is in the treatment group, and X equals 0 if the person's in the control group. So X just represents an outcome for the disease, bifurcating by whether you were in the treatment group or the control group. And the variable we care about now is this. We want to think about the number of people who got the vaccine but still got sick. That's what this sum is keeping track of, because a 1 means you got sick and we're in the treatment group. So this variable y is keeping track of the number of people who got the vaccine and yet still contracted polio. And so what we're going to do now is calculate this probability. What's the probability you would see 57 or fewer polio patients in the treatment group? That's what this is saying. Assuming the null hypothesis is true. Okay, so let's put all that together. Assuming the vaccine were not effective, what's the probability you would see 57 or fewer sick people in the treatment group, out of the 199 that got sick? So basically what you're doing is you're comparing this 57 to this 142 on some level. You're asking like, okay, if the vaccine weren't effective, like what's the probability this number is so much smaller than that number? That's what you're doing. Okay, so let's quickly walk through this. I know I've already taken too much time, but assuming the vaccine has no effectiveness, in class I would ask you this. What's the probability x equals 0? What's the probability x equals 1? So in other words, if you see a sick person, what's the probability they're in the treatment group? That's this. What's the probability they were in the control group? I present you with a child with polio and ask you, what's the probability they were in either group? And the answer is, to both of these, 0.5. Because if the vaccine weren't effective, then being in the control group versus being in the treatment group is just a coin flip. Okay, so let me say that one more time. We're assuming the vaccine is not effective. Assuming the vaccine is not effective, a sick person is just as likely to be in the treatment group as the control group. So these probabilities are both 0.5, and we are just dealing with a coin flip. So like if the vaccine weren't effective, getting the vaccine is like taking a sugar pill. It has no effect on whether you have polio or not. So all that to say, if the vaccine weren't effective, we are just coin flipping, and we are back up here actually. That's why we started with this. Except instead of flipping a coin 10,000 times, we're flipping it 199. And instead of 5227 heads, we got 57 heads. So it's like asking, out of 199 coin flips, what's the probability you only get 57 heads? That's what we're doing now. And so because we're dealing with coin flipping, I'm not going to redo this calculation here. The spread variable is, the spread of that x is still 0.5. So it's just the same calculation here. Okay, so back down here. So anyway, 0.5, 0.5, and again 0.5 because we are just coin flipping. So let's think about this. The probability of seeing 57 or fewer sick people from the treatment group. Okay. So again, we can use the central limit theorem. So this y variable is a sum, and 199 is pretty big. So we know from the central limit theorem that y is normal. We know that its expected value is the original expected value. But again, we're just coin flipping. So the original expected value of x was 0.5. It's just the average of 0 and 1, 0.5. So this is on average how many people you would expect to see who are sick in the treatment group. So again, like if there's 199 sick kids and the vaccine weren't effective, on average, you'd expect half the sick kids to be in the treatment group and half to be in control. So there's just half of the overall number. And the standard deviation is, again, 0.5 times root of the sample size, so 7.05. So this sum variable up here, this y, is a bell curve centered at 99.5 with spread 7.05. You can go to the calculator and ask it to show it to you. I guess I will because I'm here, 99.5, 7.05, below, whatever it was, 57. You can already see it. There's no 57 on here, right? So if the vaccine were not effective and we were just flipping coins, this is the distribution of sick people from the treatment group you would expect to see. Half of the sick people would come from treatment, and then we taper off in steps of size 7 or so. So it takes a lot of steps of size 7 to get down to 57. So the probability is 0, calculator says. So again, it's not literally 0, but it doesn't go past 4 decimal places. So there you go. So what does that mean? That means our p-value is basically 0, just like before. So to put it all together, let me just say out loud what you would write down to interpret that number. You would say, if the vaccine were not effective, the probability of seeing a 57-142 split like this is essentially 0. Therefore, we have very strong evidence that we should reject this default claim. Where is it? We should reject this default claim and conclude that the vaccine actually is effective. We have very strong evidence the vaccine is effective. Okay, so here are 2 examples of using the central limit theorem. It's summation form. So notice I gave you part 2 right here. Where was it? Right here. We didn't take any averages this time. We were just summing things up. And the sums were just 0s and 1s this time. So next time and moving forward, we'll look at averages and use the central limit theorem part 2. There will also be like a part 3 and a part 4, but they're all basically saying the same thing. You have some variable that it turns out if you have a large enough sample size, you get a bell curve, mean, standard deviation, you know what they are. Therefore, you can investigate all these questions like this, testing truth claims like that, or like the vaccine is effective. You can test all of those truth claims just using this calculator. This calculator will tell you what the p-value is, and so based on how big or small that is, you can reject or not reject the null hypothesis. Okay, so if any of that doesn't make any sense, please let me know. We will, of course, talk about this more on Friday if you have questions, but that's it for this section.